Welcome, everyone, to this deep dive. Today, we're jumping into the world of AI agents. You've probably heard the term, maybe interacted with them, but what are they really? How do they work under the hood? And why is everyone saying they're, so important for the future? We're going to unpack all of that today.
That's the plan. And for this, we're drawing on some great material, specifically excerpts from AI Agents Conceptual Understanding Deep Dive. It's a really solid piece that gives a structured overview based on current research.
Right. So our mission here is basically to give you a good conceptual handle on these AI agents.
Yeah.
We're talking definition,
Yeah.
components, the different types, the principles they run on, and where they're actually being used.
Exactly. And we want to do it without getting too bogged down in the weeds, make it clear and insightful.
Because these aren't just lab experiments anymore, are they?
Not at all. They're increasingly part of our world. Think healthcare, finance, logistics.
So driving cars, those chatbots you talk to online?
Precisely. And what's fascinating is how they've evolved. They started as, fairly simple rule-based programs now. We're seeing sophisticated systems making complex decisions pretty much on their own.
Okay, let's dive in then. The core idea, what is an AI agent, fundamentally?
Well, at its heart, an intelligent agent is, let's call it an entity. Its job is to operate within some kind of environment. It perceives that environment using sensors, and then it acts on it using actuators, all to achieve certain goals.
Perceive, act. Okay, what makes that different from regular software?
It's the continuous cycle. Perceive, think, act. It's always running. It takes in information, processes it, acts, which changes the environment, which leads to new information. It's a loop.
Oh, okay, not just a one-off script execution. It's
Yeah. dynamic. Exactly. And that think part is often about its goals. Goal-directed behavior is key. Agents usually have some objective function or performance matter, basically, what success looks like for them. They try to make choices that get them closer to that goal.
Like finding the best route on a map.
That's a good example. Or winning a game. There's even this term from economics, the rational agent, which just means an agent that acts optimally to achieve its goals based on what it knows.
Right, makes sense. So sensing, acting, and a goal. Let's break down the construction. What are the building blocks?
Okay, think of it like modular parts. First up, sensors, or you might hear perception module. This is how the agent gets info. We call these bits of info perceps from its environment.
Like cameras on a robot. Maybe text input for a chatbot.
Exactly. Physical sensors like cameras, LiDAR, microphones, or software ones like APIs, reading data, UI inputs. And it's not just the current percept, but the whole history, the percept sequence that can matter. And AI techniques like NLP for understanding language or computer vision for images are often crucial here to make sense of the raw data.
So sensors are the input channels. The eyes and ears, sort of. What about the output? How do they do things?
That brings us to the actuators, or the action mechanism. This is how the agent actually influences its environment.
So the robot's motors or the arm that picks something up?
Yep. Physical things like motors, robotic arms, speakers, or software actions, making API calls, writing to a file, displaying something on screen. This is how the agent expresses its agency. It makes things happen. And being able to call external tools or APIs, that's becoming super important for modern agents. Extends what they can do massively.
Okay, input via sensors, output via actuators.
Yeah.
But the magic happens in between, right? The decision part.
Absolutely. That's the decision-making engine. You might also hear it called the reasoning engine or cognitive architecture. It's the brain. This is where sensor data gets processed, often using memory and learned knowledge to choose the next action.
And I guess this brain can be simple or really complex.
Hugely variable. It could be simple if-then rules, or complex search algorithms, planning, maybe calculating the utility or value of different actions, or it could involve machine learning, probabilistic reasoning, even those big, large language models we hear so much about.
Wow, okay, so lots of different ways to build that decision engine.
Yeah, and mathematically you can think of the overall agent function as something that maps the entire percept history to a specific action right now.
You mentioned memory. Why is that important? Can't it just react to the present?
Well, sometimes. But often memory is vital. Agents need it for context, especially if the environment is only partially observable, meaning they can't see everything relevant all at once. Memory helps fill the gaps.
Like remembering where it's already been. if it's a vacuum cleaner robot.
Exactly. Or remembering what was said earlier in a conversation. And crucially, memory is needed for learning from past experiences. We can talk about short-term memory for current context, long-term for stored knowledge, episodic for past events, semantic for general facts.
Lots of types of memory, just like us in a way.
Sort of. And how that memory is organized and accessed is really key to how well the agent performs.
Makes sense. And you mentioned learning, too. We'll circle back to that, definitely.
Yeah.
But first, this interaction with the environment. It's a two-way street.
Totally. It's dynamic, reciprocal, perceive, actuates, environment changes, new percepts. It's a constant loop.
Right.
And the agent's underlying structure, its sensors, actuators, the whole setup, we call that the architecture. And the logic inside the decision-making part, that's the agent program. Together, they define how that interaction happens.
And they all have to work together smoothly.
Yeah, they're tightly linked. You could have the smartest brain, but if your sensors are poor, you're limited. Bottlenecks can happen anywhere.
And the environment itself, it's not always like a physical room.
Good point. It's quite abstract, could be physical space, sure. But also a website, a software system, a simulated world, even a social network. Defining the boundaries of that environment and what the agent can sense and do within it is a really fundamental design step.
Okay, got the basic structure.
Okay.
But you said there were different types of agent brains, different architectures.
Yes, exactly. We can sort of classify them by how sophisticated their thinking is. There's a common taxonomy. Think of it as levels. Simple reflex, then model-based reflex, goal-based, utility-based, and overarching all of these, learning agents.
Let's start simple then. Simple reflex agents.
The most basic. They operate only on the current percept. No memory of the past. They use simple condition action rules like, if dirty, then clean.
So very reactive, like a thermostat that just turns on when it's cold.
Perfect example. Or an automatic door. They react fast to simple things. But the big limitation, no memory. So in environments where they can't see everything, partially observable ones, they get stuck. They might repeat actions uselessly or make bad choices because they lack context. Very limited intelligence, really.
Okay, so simple stimulus response. What's the next step up?
That would be model-based reflex agents. These are smarter because they maintain an internal model of the world. This model helps them keep track of things they can't directly see right now based on past perceptions and their own actions.
So they have some kind of internal state, a memory of how the world is.
Exactly. They still use rules, often, but the rules act on this internal state, not just the raw input. This makes them much better in those partially observable environments.
Like the robot vacuum remembering the cleaned areas.
Precisely. Or a smart thermostat learning your schedule. Even navigation systems using traffic updates rely on a model of the road network. The catch is, the agent is only as good as its model. Building and updating complex, accurate models is hard.
Right. The model could be wrong or outdated.
Okay.
Model-based. Then you mentioned goal-based agents.
Yep. These take it another step. They have a world model, plus explicit goal information. They know what state they want to achieve.
So they don't just react or maintain a state, they actively try to reach a destination.
Exactly. Their decision-making considers the future. They use planning or search algorithms to figure out sequences of actions to reach their goals. They reason about the consequences of actions. If I do X, then Y will happen, which gets me closer further from my goal.
That sounds much more flexible. Like planning a route?
Route planning is a classic example. Or game AI trying to capture a flag. Project management software planning tasks. The advantage is flexibility changes the goal. The behavior changes. They have explicit knowledge driving them.
Limitations.
Planning and search can be computationally heavy, especially for complex goals. And they often treat goals as binary, either achieved or not. They might not care how efficiently they got there, just that they did.
Okay, so they find a path, but maybe not the best one.
Right. Which leads us to utility-based agents.
Utility.
Yeah.
Like usefulness.
Sort of. They refine the goal-based idea with a utility function. This assigns a numerical score, a preference level, to different states of the world. How good or desirable is this state?
So it's not just goal reached, yes, no, but how good is this outcome?
Exactly. Their aim is to maximize expected utility. They consider not just the outcome, but the probability of different outcomes, dealing with uncertainty. This lets them handle trade-offs between conflicting goals. Do I take the faster route with more traffic risk or the slower, safer one?
Okay, that sounds much more nuanced, like real-world decision-making.
It is. Financial trading agents balancing risk and return are a good example. Dynamic pricing systems, personalized recommendations that weigh different factors. If the utility function accurately reflects the real performance measure, These agents are considered highly rational.
What's the downside? Sounds complicated.
It can be. Defining a good comprehensive utility function is often really tricky, and calculating that expected utility can be computationally intensive.
Right. So we've got reflex, model-based, goal-based, utility-based. What about learning agents? You said they overlay these.
Yeah, learning agents aren't really a separate architecture in the same way. They're an enhancement to any of the others. The defining feature is a learning element. This component allows the agent to improve its performance over time based on experience.
So any of those types could potentially learn.
Absolutely. A learning agent typically has 4 conceptual parts. The performance element, which is like the original agent architecture, making decisions. The learning element itself, which modifies the performance element. A critic, which evaluates how well the agent is doing, providing feedback. And sometimes a problem generator, which suggests new exploratory actions to try.
Why a problem generator?
Yeah.
Just trying random stuff.
Sort of. It encourages exploration to find potentially better ways of doing things, rather than just sticking with what it already knows. It helps avoid getting stuck in a rut. The big advantage of learning is adaptation. They can work in unknown environments, improve beyond their initial programming, adapt to changes.
Examples.
Fraud detection systems that adapt to new scam tactics, content recommendations, learning your tastes, speech recognition, adapting to accents, adaptive thermostats.
Downsides to learning.
Learning can be slow, needs data, performance might be a bit erratic while it's learning, and how well it learns depends heavily on the learning method and the quality of the feedback. There are also more complex types, like hierarchical agents that break problems down, and multi-agent systems where many agents interact, but these are maybe beyond our scope for today.
That's a fantastic breakdown. And the source material has a table summarizing these, which is helpful. Okay, let's pull back a bit. What are the guiding principles behind how these agents operate intelligently?
There are a few core concepts. We've touched on perception sensing the world, and crucially, interpreting that raw data into something meaningful. Accuracy here is key.
Right. Seeing isn't enough. You need to understand what you're seeing.
Exactly. Then there's action selection, choosing what to do based on perceptions and goals. That's the agent function or program in action, varying by architecture. Then you execute that action via actuators.
Perceive, decide, act. Seems straightforward. What else?
Rationality. This is a big one in AI. It doesn't mean thinking like a human or having feelings. It means acting in a way that's expected to best achieve your goals, given what you know and perceive.
Best expected outcome, based on that performance measure you mentioned.
Precisely. It depends on the performance measure, the agent's prior knowledge, what actions it can take, and its percept history. Importantly, rationality is not omniscience. It doesn't mean knowing everything. It's not perfection.
It can still make mistakes if it has bad information.
Exactly. Or if its choices are limited. Rationality can even involve choosing to gather more information if that's expected to lead to a better outcome later. Exploration can be rational.
Interesting. Utility-based agents seem like the poster child for rationality then?
They definitely embody the principle, clearly, trying to maximize that expected utility.
Okay, rationality. And the last principle.
Autonomy. This is about the degree of independence. How much can the agent operate without direct human control?
It's a spectrum, right? Not just on or off.
Definitely. From semi-autonomous needing supervision to fully autonomous. And there's a strong link to learning here. Learning allows an agent to rely less on its initial programming, compensating for incomplete knowledge, which boosts autonomy.
Is autonomy the same as rationality?
Good question. No, rationality is about the quality of decisions, doing the right thing. Autonomy is about the independence of decisions. Ideally, you want rational autonomy agents that make good decisions independently.
So perception, action selection, rationality, autonomy, these are like the design pillars.
Exactly. When you build an agent, you have to consider how will it sense, what can it do, what defines success, rationality, and how independent does it need to be.
This helps frame the design. I know there's a specific framework mentioned in the source, PEAS, for defining the task itself.
Yes, the PEAS framework. It's a really useful way to specify the task environment for an agent. Helps everyone get on the same page. PEAS stands for performance measure, environment, actuators, and sensors.
Okay, let's break that down. P performance measure.
That's the criteria for success. How do we judge if the agent is doing a good job? Safety for a self-driving car, profit for a trading bot, score in a game. It has to be measurable.
The environment.
This is everything outside the agent it interacts with. The road for the car, the stock market for the bot, the game board, and crucially, the properties of that environment matter a lot.
Actuators.
How the agent acts on the environment. Steering wheel, brakes, accelerator for the car, placing buy-sell orders for the bot, moving pieces for the game AI.
And S sensors.
How the agent perceives the environment. Cameras, radar, GPS for the car, market data feeds for the bot, seeing the board state for the game AI.
So P's gives a structured definition of the job. And you mentioned the environment's properties are key.
Yes, the source details several ways to classify environments, which really impacts agent design. Is it observable, fully or partially? Can the agent see everything it needs? Agents, single or multi? Is it alone or interacting with others, cooperatively or competitively?
Like chess is multi-agent competitive.
Yeah, exactly. Is it deterministic or stochastic? Is the outcome of an action predictable? Or is there randomness involved, episodic or sequential? Is each decision independent, or do past actions affect future states? Driving is very sequential.
Right, one turn affects where you are next.
Then, static or dynamic. Does the environment change while the agent is thinking, or does it wait? Traffic is dynamic. Chess is static between turns. And finally, discrete or continuous. Are states and actions distinct things, like chess moves, or are they real valued ranges, like steering angle?
Wow, okay. Lots of dimensions, and the source walks through examples using P's, right?
Yeah, like an automated taxi. Performance might be safety, speed, legality, comfort. Environment is roads, traffic, pedestrians, partially observable, multi-agent, stochastic, sequential, dynamic, continuous. Actuators are steering, accelerator, etc. Sensors are cameras, LiDAR, GPS.
That really spells out the challenge. How does P's connect back to rationality?
You can't define what's rational, doing the right thing, without knowing the P, what's the goal. And the E, A, and S, what's the context? What can it perceive and do? Agent intelligence isn't absolute. It's relative to its specific P specification.
Okay, that clarifies the context. Now, a big question, AI agents versus just regular software. What's the real difference? People might think all software acts based on input.
It's a good question. The core difference really boils down to adaptability and learning. Traditional software follows predefined static rules. It does what it's programmed to do. Change requires a human developer changing the code.
Rigid.
Right. AI agents, especially the more advanced ones, can learn from experience. They can adapt their behavior over time to new situations, changing conditions, without explicit reprogramming for every scenario. Flexibility versus rigidity.
That seems like a huge distinction. What else?
Goal orientation and proactivity. Many AI agents are designed around achieving goals. They can plan sequences of actions autonomously. Some can even be proactive, taking initiative towards their goals, not just reacting to commands. Traditional software usually executes fixed sequences or waits for direct instructions.
So less passive, more driven.
Kind of. And their environmental interaction is often richer. Agents deal with potentially complex, noisy, real-world data via sensors. Traditional software usually has more defined, predictable interfaces and data inputs.
And autonomy, which we mentioned.
Yes, that degree of independent decision-making. Traditional software generally needs more human oversight or direct commands. So fundamentally, it's a shift from purely procedural execution to more adaptive, goal-driven, somewhat independent behavior.
Got it. And I've heard this term agentic AI popping up more lately. Is that just a fancy synonym for AI agent?
Not quite, though they're obviously related. Agentic AI usually points to systems showing a higher degree of these agentic properties. Think of it as maybe a subset or the high end of AI agents.
Higher degree. Like more autonomous,
Yeah.
more proactive.
Exactly. More autonomy, more sophisticated reasoning and planning, handling complex, multi-step tasks, more proactivity, advanced learning, better tool use, using external APIs or software effectively, maybe even collaborating with other agents.
So the core principles of agency, but dialed up maybe thanks to things like LLMs.
That's a good way to put it. It distinguishes these really advanced systems capable of complex autonomous tasks from simpler agent concepts. It's about realizing those principles at a higher level.
Okay, that clarifies the terminology.
Yeah.
This is great conceptually. Let's ground it again. Where are these agents actually showing up? Real-world examples.
Oh, they're becoming quite